You know, we're surrounded by shapes all the time, but have you ever really stopped to think about how we can describe them with the precision of math? I'm not just talking about equations for simple things like circles or squares. I mean, the very essence of any curve, any surface. Well, today we're diving into the incredible field of differential geometry, which pretty much gives us a secret language to understand the form of everything around us. It all starts with a question that sounds so simple, you might have asked it as a kid, but it's actually incredibly deep. What does it really mean for something to be curved? I mean, you can see it, you can feel it, but how do you pin it down with a number? How could you prove mathematically that a sphere is more curved than, say, a gentle hill? This is the central puzzle we're going to try and solve. So if we want to understand these big, complex, curved surfaces, we have to start with the absolute basics. And the simplest curved thing you can think of is just a line that isn't straight, right? So let's start there. Let's build our basic toolkit by figuring out what a curve actually is in the language of mathematics. Okay, so in the world of math, a curve is just a function. The best way to think of it is like a recipe. You plug in a number, we'll call it t for time, and this function, this recipe, gives you back a specific point in 3D space. As you smoothly change t, that point moves and it traces out a path. Now, the key word on this slide is differentiable. It sounds a little scary, but all it really means is that our path is smooth. No sudden teleportations, no sharp, jagged corners, just a nice, continuous, flowing line. And this quote just nails it. This is the perfect way to picture what's going on. Forget the formal definition for a second and just imagine a firefly zipping around in the dark. The glowing trail that it leaves behind. That's a curve. And our function, alpha of t, is just our way of writing down the firefly's exact x, y, and z coordinates at any given moment. And just like that, we've got our first tool. All right, so we have a tool for describing one-dimensional curves. Now it's time to level up. We're going to go from lines to two-dimensional surfaces. But to do that, we need a totally new way of looking at things. Instead of looking at an object from far away, we're going to zoom in, like really far in. This right here is the foundational insight of all of differential geometry. Just think about the Earth. To us, just standing around on it, it seems pretty flat, right? But we all know it's a giant curved sphere. Well, this local flatness is true for any smooth surface, whether it's a basketball, a donut, or the hood of your car. So how do we capture this idea of a local flat patch with math? We use a brilliant tool called the tangent space. Imagine taking a perfectly flat, stiff sheet of paper and trying to place it on a basketball. It can only touch the ball at a single point, right? Well, that flat sheet of paper is the tangent space at that point. It is the best possible flat approximation of the curved surface, but only at that one tiny spot. And now we have all the tools we need to finally tackle our main question. We've gone from simple curves to understanding the local properties of surfaces. It's time to reveal the secret language that lets us finally measure curvedness. The answer comes down to this: a single, incredibly powerful number called Gaussian curvature, which we usually just write as the letter K. And the absolute key to understanding this is the word intrinsic. Imagine you're a tiny two-dimensional ant living on a vast, curved sheet of paper. You can only walk forward, backward, left, or right. You have no concept of up or down. Gaussian curvature is the number that would tell you your world is curved, using only measurements you could make from within your 2D world. It's a measure of the shape's own built-in geometry. And as you can see here, this Gaussian curvature basically comes in three flavors. You've got a surface like a sphere, which is curving away from you in all directions. That has positive curvature. Then you've got a totally flat plane, which, no surprise, has zero curvature. But then there's this really interesting case, a shape like a saddle. It curves up along the versus spine, but curves down where your legs would go. That's the classic example of negative curvature. This one number, k, tells us the entire story of the shape at that specific point. So we now have a way to find a number, k, that describes the curvature at any single point on a surface. That's powerful. But this is where the story gets truly mind-blowing. We're about to see how all these tiny, local measurements can actually reveal a huge, global secret about an object's overall shape. This is the big question. Let's go back to that tiny bug. If you, as the bug, walked all over your world, measuring the Gaussian curvature at every single step, could you piece together enough clues to figure out the overall shape of your universe without ever leaving it? Could you tell if you were living on a sphere or maybe on a donut?
The answer is a resounding yes, and it's all thanks to the incredible Gauss-Bonnet theorem. What it says is that if you add up all of the local curvature values over an entire surface, it's a process mathematicians call integration, the grand total you get isn't some random number. No, it's a value that is directly locked to the surface's topology, which is just a fancy way of describing its most fundamental properties, like how many holes it has.
So get this. For any sphere, it doesn't matter how big or how small, if you add up all the Gaussian curvature everywhere on its surface, you always get the exact same number, 4 pi. A tiny, tightly curved sphere has really high curvature, but over a small area. A huge, gently curved sphere has low curvature, but over a much larger area. They balance out perfectly to equal 4 pi every single time.
But now look at this. For a torus, a donut shape, the total curvature is always 0. How? Well, the positive curvature you find on the outside of the donut is perfectly canceled out by the negative, saddle-like curvature you find on the inside. That number, 0, is a direct mathematical signature of the donut's single hole. The local geometry point by point has just revealed the global topology. It's incredible.
Now, this is way more than just a beautiful, abstract mathematical idea. Understanding this language of shape has completely transformed our world, from the way we travel across the planet to our very understanding of the cosmos itself.
Differential geometry gives us something called geodesics, which are just the shortest paths on curved surfaces. That's exactly why airplane routes look like big arcs on a flat map. It's also the mathematical engine behind Einstein's theory of general relativity, which describes gravity not as a force, but as the actual curvature of space-time. And yeah, every single time you see a stunning 3D animation in a movie or you play a video game, you are looking at differential geometry in action, defining and manipulating all those complex digital shapes.
So, just think about where we started. We asked a really simple question. What does it mean to be curved? And the answer led us down this incredible path that connects a single point on a surface to its overall shape and connects a simple flight path to the very fabric of space-time. It really makes you wonder, doesn't it? If geometry is truly the language of shape, what other secrets of the universe are written in it, just waiting for us to figure out how to read them?